Hi, class. So this is our it's our third lecture in chapter 19, but the second part of chapter 19.2. And in this chapter, we're going to explore the structures of complex ions and also a topic called isomerism. And this worksheet we're going to do is shown here. It's worksheet 34. And this is a concept map of what isomers are, what kind of isomers there are in complex ions. And so we'll be doing this at the end. So I'm going to share my screen and we will get started on the PowerPoint. All right. We'll start off with our objectives. And previously in part one, we looked at what makes a coordination compound and the kind of bonding that occurs in the complex ion. We call that coordinate covalent bonding. It's where, and we said the complex ion is made up of a ligand and a transition metal ion. And we also talked about how we name those and how we write the formulas. So in the worksheet, we'll be practicing that also. But in this chapter, we're going to describe the structures of these complex ions. And we know when the ligands form the ligands, we can have 2, 3, 4, 5, multiple numbers of ligands that are called the coordination sphere. Remember when we wrote the formulas of a complex ion, we put the complex ion within brackets. Well, all of the atoms within the brackets are in the coordination sphere. Okay, so we'll be talking about the coordination sphere this time. And remember the complex ions contain ligands that we call monodentate, bidentate, and polydentate ligands. Lastly, we'll look at what we call isomers, which are, we'll define what an isomer is, and look at the different kinds of isomers that one finds in complex ions. So this is a figure out of your book, and it shows 3 types of complexes. So in the first complex, we have 2 ligands, 2 ammonia ligands, complex to the silver 1 ion. And because there are just 2 ligands complex to it, there are 2 connection points to the central atom, we call that the coordination number. So in the case of the silver ion, or the silver 1 complex with 2 ammonias, the coordination number is 2 because we just have 2, to circle these, we have 2 nitrogens connected to that central silver atom. So that coordination, that makes it a coordination number 2. So the coordination number, the reason why that's important, because the coordination number determines what the structure is, what the shape of that complex ion is. So we talk about structure, we're talking about the shape of the ion. And if you only have 2, if you have a coordination number of 2, the shape is going to be linear. So we look at that. And this goes back to what you learned previously about molecular shapes back in chapter 7.6. And it was called the VS-EPR model. So I'll write that here, the VS-EPR model of molecular shape. And if you're a little fuzzy on that concept, you might want to go back and look. It's in chapter 7.6. And the second edition of this book says the VS-EPR model. They talk about linear shapes. They talk about trigonal planar, talk about tetrahedral, octahedral, and All those are shapes that we're going to look at in this lecture. So in the second example here, we have a complex ion made up of 4 ligands. And these are chloride ligands, in this case, connected to a copper 2 plus ion. And when I say copper 2 plus ion, you should know how I arrived at that copper 2 plus. So if you don't understand that, think about it. Think, well, how does Chuck know that this copper is a copper 2 ion? So anyway, there's 4, this coordination number is 4. And so that makes a tetrahedral structure. So in the case of the silver ion, it was a linear structure. In the case of the copper 2 complex ion, it's a tetrahedral structure. Now we write tetrahedral to try to show in a 2-dimensional, you're looking at this screen, which is 2-dimensional, but all these shapes are 3-dimensional. So to demonstrate the 3-dimensionality of the tetrahedral shape, we use different types of bonds. So the straight bond here, these bonds that are written how you normally write a bond, just a line. The bond that's a line indicates that that connection between the copper and the chloride is in the plane of the paper. The wedge connection, the chloride to the copper with a wedge bond, means it's coming out of the paper. It's towards you. So if you're looking at this bond is coming at you. And then the dotted line bond means it's going behind the plane of the paper. So if you haven't seen this before, this what it means, and we're going to be, when we get to organic chemistry, many of the organic compounds have this tetrahedral shape around the central atom, and this is how you write the bonds to try to illustrate the 3-dimensional, I can't say that word, dimensionality, I don't know if that's a word or not, of the shape. So, and lastly, in this example, in this slide, we have a complex ion with 6 ligands, and the 6 ligands take on an octahedral shape. So you see the ligands themselves are in the corners of an octahedron, which is an 8-sided figure. It's like 2 square pyramids face to face. You might think of it as like sort of a diamond shape. But anyway, the ligands are pointing to the corners of the octahedron. And again, we have a structure here with dashes and wedges. So the wedge, the water, these are aqua ligands or water molecule ligands. And the ones with the wedges are coming out towards you, and the ones with the dashes are going behind you. They're actually in a plane that's horizontal to the plane of the screen you're looking at. Excuse me, not horizontal, perpendicular. So the dashes and the wedges that implies a plane that's perpendicular to the plane of your screen that you're looking at. And so that would be called a octahedral complex. So just to summarize, if you have 2 ligands or a coordination number of 2, you end up with a linear structure. If you have 4, you have a tetrahedral structure. And these are the most common. And if you have 6, it's octahedral. Now there's another structure if you have 4, and that's a square planar. So square planar and tetrahedral are both very common. So these are the most common types of ligands, your 2, 4, 6. Coordination numbers, the most common coordination numbers, and the most common structures that you see. So the I guess the one that's not shown is the square planar. It should have had a square planar here, but a square planar would look like this. So you have the metal ion in the middle, and you just have ligands off on the corners of the square. Okay, that's a flat. That's in a plane. So let's move on. So when you have a bidentate ligand, and here's a common one. This is ethylene diamine. So the symbol for this, when we're writing our structure, is En. So that's the symbol used if you're writing the formula. You use an En for this ethylene diamine. This is an organic compound, by the way. So it's made up of carbon, hydrogen, and nitrogen elements. And anyway, we said to be a ligand, you have to have a lone pair. So in this ethylene diamine, the nitrogens on each end of this molecule has a lone pair, which are shown. So those are that's the pair of electrons that forms the coordinate covalent bond with the central metal atom. Well, if you have three of these, you can form an octahedral or a ligand with a coordination number 6. So we have 1, 2, 3, 4, 5, 6 nitrogens that are coordinating to that central cobalt atom or ion. So the coordination number, and I'll use Cn for coordination number. Coordination number is 6 here. So since it's a coordination number 6, it forms an octahedral complex. So if you can see those bonds, these bonds have the same same designation. I mean, the vertical bonds are just straight lines, which means in this plane. Then the horizontal, and then the bonds horizontally, we have 2 wedges and 2 dashes. The dashed bonds are going behind the plane of the screen, and the wedge bonds are coming out of the plane of the screen. So this is how a bidentate ligand can form a complex ion with a coordination number 6 and form an octahedral shape. So I think that's, if you look, let me move my, I don't know if you can see this. I have this thing here kind of in the way, but at the very bottom, the comment C says coordination number 6. So this ethylene diamine is a very common ligand in complex ions. In fact, organic molecules are common ligands. We'll see a few more examples of these as we go on. Oops, let's go on. Not sure what's going on here. I can't seem to change screen. Come on. Do I touch it? Oh, there we go. Okay. So here's another organic molecule. And this is a complex ion with a coordination number 4. So again, we have 4 nitrogens with a complex to the central iron. This is hemoglobin. And it's kind of part of hemoglobin, actually. There's more of these in actual hemoglobin. It's more complicated than that. But it's a very complicated organic compound with 4 nitrogen ligands. This would be a tetradentate ligand, this big molecule here. This whole thing is one molecule. That's one molecule with a iron in the middle, complex to the 4 nitrogens in that molecule. So again, this would have a coordination number of 4. And the shape would be, this is an example of a square planar. Okay, so this, we have 4 coordinate covalent bonds to that central iron. And this iron can actually have, it can be an iron 2+ ion or iron 3+ ion in hemoglobin. So like I said, organic compounds, there are many organic compounds, especially in biological systems, that form complexes to central to transition metal ions. So here's another one, coordination number 4, square planar. This is platinum's in the middle. And this is actually an amino acid. So this is the amino acid is called glycine. And we have two ligand atoms in this molecule. Actually, we have four, but there are two that are connected, or three. There's any nitrogen, remember, any atom with a lone pair can be a ligand. So in this molecule, we have the nitrogen and the oxygen. And again, this is another ligand with coordination number 4, and this would be a scored planar. So here's a summary of the different kinds of shapes you get with the different coordination numbers. So coordination number 2, we get linear structure, complex ion with a linear structure. Coordination 4, we get scored planar tetrahedral. Coordination 6, octahedral. Those aren't all the coordination numbers though. So you can go up to 7 and 8. And these are some of the shapes that you get with coordination numbers 7 and 8. They're not very common, so we won't be covering those, but I just wanted to show you those. These are in the book also. And here's, if we go up, here's a more extensive summary page that shows the name of the molecular geometry, the different coordination numbers from 2 to 8, and the different geometries you get with those. And there's some example complex ions or complex compounds shown in the right-hand column. But the most common ones are coordination numbers 2, 3, or 4. So I didn't talk about 3, but if you have a coordination number 3, you get a trig little planar. And that's a flat molecule with 3 coordinate covalent bonds to the central atom. So those, the most common, as I said previously, are 2, 4, and 6. Those are the ones we'll be looking at in the rest of this chapter. So this slide shows 3 examples of octahedral complexes with coordination number 6. All of these have coordination number 6. And I don't know, I think the point of this is that even though all these have different numbers of, these show coordination compounds. So it's a complex ion plus the counter ion. So the shape is only determined by the ligands attached to the transition metal. That it's only determined by the ligands or the elements, the molecules, the species within the coordination sphere. Remember I told you the coordination sphere is within these brackets. So the shape is only determined by what's within the coordination sphere. And when we get to isomers, this becomes important when we talk about isomers. And when we talk about structures, the structural component of a coordination compound is really a structure that's that occurs, we're talking about the structure of the complex ion. Now the structures, these coordination compounds, because they're ionic, they form crystals. So if they're not in solution, you'd have a crystalline structure. There's lots of different crystalline structures. We're not going to talk about the crystalline structure of coordination compounds. So this lecture is not about that. So here's a coordination number 4. So there's 2 examples of what the structure you get with coordination number 4. So we have the tetrahedral on the left and the square planar on the right. So let's look at this topic called isomers. So what are isomers? So isomers are substances that have the same formula. And when we're talking about isomers, we are talking about the formula of the coordination compounds, the whole compound, so the formula of the whole compound, or the formula of the complex ion. So some isomers deal with the whole compound. Some isomers only occur within the actual complex ion. So I'll try to point that out as we're going through. So what are isomers? Isomers are substances that have the same molar mass but different structures. Okay, so the same molar mass means they're made up of all the same elements and the same number of atoms of each element. And so if you have something made up of cobalt and nitrogen and hydrogen, well, the isomers are substances that have the same number of atoms of each element. So the molar mass is the same, but their structure is going to be different. And so in the case of coordination compounds and complex ions, we're going to talk about 5 different isomers. So the 5 different isomers are here. So that one isomer here. This particular isomer, ionization isomerism, coordination isomerism, it's the same name. When I taught this previously, I call this a coordination isomer, but your book adds ionization isomer. So I want to include both of those, and homework has this ionization isomer. So it's 2 names for the same thing. There's a linkage isomerism. That's another kind of isomer, a linkage isomer. There are geometric isomers. There are actually stereoisomers. The three isomers that fall under this broad topic called stereoisomerism. So we have geometric isomers, facial, meridional. I don't know how to say that word. I'll write it. It's meridian with AL and then meridional isomerism. So facial and meridional, and then optical isomerism. So we have 1, 2, 3, 4, 5 different isomers we're going to talk about in this part of the lecture. And they're broadly grouped into structural. So the coordination isomers and the linkage isomers are both called structural isomers. And structural isomers, as the note says there, have different bondings. So the bonds have changed. And in stereoisomers, you have the same bonds, the same connections, but the arrangement, the spatial arrangement is different. And so if you have something like a cobalt with 6 amines around it, there aren't too many ways you can change the arrangement. But if you have cobalt with 4 amines and 2 chlorines, those chlorides, the chloros, so you have 6 amines, 4 amines and 6 chloros around the cobalt. Well, the arrangement of the chlorines and the amines around that cobalt can be different, and that's where you get the stereoisomer. In the structural isomer, you actually have different connections to the central atom. So we'll look at the difference there. So that's an important difference. The thing is that when we talk about structural and stereoisomers, these occur in organic chemistry too. So when we get to our chapter 20, we're going to again look at the different kinds of isomers that you can get from organic compounds. And in organic chemistry, there are lots of isomers. We'll separate the organic compounds into structural and stereoisomers. And the structural isomers are sort of I guess, linkage. We have different names for different kinds of structural isomers in organic. But this part, that I've outlined here, the broad classification of isomers, structural and stereo, also apply to organic chemistry. Well, lastly, each isomer, to distinguish an isomer, because the formulas are the same, right? Same molar mass, same formula. That means if you just write a formula that includes just the elements and how many atoms there are of each element, all the isomers would look the same. So to distinguish between isomers without having to draw the structure each time, the structures are different. I mean, if you drew out every atom and how they're connected, it would look different. Is that each isomer has a unique name. And so I'll be talking a little bit about these names. We're not going to have to name them, but I want to point out some distinctions between the names. I'll point those out. So let's start off, let's go back here. We're going to start off looking at structural isomers, and we'll look at coordination and then linkage, and then we'll go into stereoisomers to finish up this unit, then we'll do the worksheet. Okay, structural isomers and coordination compounds, and we'll look at the coordination isomers. So we said coordination isomerism is also called ionization isomerism. And that's where you look at the structure of the complex ion. Here's two complex ions that are coordination isomers. So we have chromium with 5 amines and 1 sulfate, and then the counterion is bromide. Well, what happens is the bromide is a negative ion, the sulfate's a negative ion. They can switch places. So then you have a chromium with 5 ammonias, and the bromide is a ligand now, and the sulfate's outside the coordination pair. So actually, in a coordination isomerism, the complex ion changes. So the complex ion actually changed. In this case, the charge of the complex ion changed. So the chromium in this case is a 3+ chromium. So this is a chromium 3 in both cases. That doesn't change, can't change that. Chromium 3. But the sulfate in this case is a 2-, so the complex ion here has a 3+ and 2- is a +1 charge. The complex ion is a 1+ on the left side, and the bromide is a -1, so the complex ion on the right side is a 2+ ion. And that matches the counter ion. So if for the coordination compound, remember those are neutral. So if the complex ion is a +1, the counter ion has to be a -1. That's what bromide is. And on the right side, the complex ion is a 2+, so the sulfate has to be a 2-. I'm not keeping consistent with my convention for charges. When you talk about charges, should have the number and then the sign. Oxidation number is the sign and then the number. Remember that we talked about that previously. But anyway, that's so in a coordination isomerism, the actual structure of the complex ion changes, but the overall molar mass, the number of atoms that are in the compounds, does not change. So those are identical. The number of atoms in the coordination compound is the same. So the ionization, well, so I said ionization, I said because the charge of the complex ion, that's not what ionization means. Ionization means that when you put these in solutions, you get different ions in solutions. So this isn't quite right. But sometimes the charge of the complex ion does change. So it's called an ionization isomerism because in solution, the ions actually have changed. On the left side, you have a complex ion with a +1 charge and a bromide ion. On the right side, when you put it in solution, you get a 2+ complex ion and a 2- counter ion. So I don't know if I have any more examples of those. We'll see. But anyway, the other kind of isomerization is linkage isomerism. And the case of linkage isomerism is that the ligands within the coordination sphere are the same, but the attachment of ligands. So it might be a ligand like we saw some ligands, some of the bidentate ligands have two atoms that can connect. In that one case, if you remember, there was a glycine. I told you there's a molecule called glycine that had a nitrogen and an oxygen. And so when you have two different ligands like that, a nitrogen or two atoms can act as ligands within a ligand. If you can get say a complex ion with a nitrogen connected to the central ion, you get a different complex ion with the oxygen connected to the complex ion. So that's what linkage isomerism is. We'll see some examples. So, so here is an example of, let me move some of this stuff. Okay. So here's an example, another example of coordination isomerization. So in this case, we have pentaamine cobalt chloride complex ion with the bromide as a counter ion, and then the bromide and the chloride switch places, and you have a cobalt hexaamine bromide complex ion with the chloride as a counter ion. Now in this case, so the ions in solution have changed, they're actually different ions, but the charge of the complex ion hasn't changed. Oh, and here's the example we had previously. So I said sometimes the charge of the complex ion has changed. So this is an example of a linkage isomerism. And in this case, we have a nitrite ion. So the nitrite ion is O2 minus. Let me write this. Let's see, so we have the ligand that's changing is a nitrite ion. And the nitrite ion looks like this. If we draw the structure of the nitrite ion, whoops. Let me go back. Okay, nitrite ion, I think I can write it. So it's like this. O in brackets, it's a negative, and it has a lone pair. On the nitrogen. And it has, remember, lone pairs on the oxygen. I don't know if I can draw these. This is a pretty sensitive stylus I'm doing. If I press too hard, there we go. Okay, there's the lone pairs of the oxygen. So this can form coordinate covalent bond with the central atom through the nitrogen or through the oxygen. And that's what we have here. So these examples at the bottom, we have a cobalt central transition metal ion, and we have 4 amines, and we have 1 nitro. So this is called, so this is the coordinate covalent bond is through the N, the way it's written. And in the second example, the coordinate covalent bond on the nitroso ion is through the, or the nitrous ion is through the oxygen. So how do we call these? So in the case of the linkage through the nitrogen, it's called the nitro group, called nitro. And when the linkage is through the oxygen, it's called the nitrito. And I have a picture on the right is what it looks like. This, if you look at the coordination number, this has 4 amines, a nitrous ion, and the, or excuse me, nitrite. I'm getting mixed up here. This is nitrite. Let me write this down. The ion is called nitrite. And we have a chloride, a nitrite, and 4 amines. So the coordination number 6. And so if you look at our structures over on the right, they're octahedral structures. So we didn't show the other ligands, we just showed the nitrite. And in the example A, that forms a coordinate covalent bond through the nitrogen. And that means we call that, when we name this compound, we call that a nitro. And in the second case, we have the nitrate forming a covalent bond through the oxygen, and that's called a nitrido. So if we name these, it would be the tetraamine, and then it would be chloro. Remember, we do these alphabetically. Tetraamine, chloro, nitro, cobalt, and it's a cobalt 2 ion. So it'd be cobalt 2. The second case would be tetraamine, chloronitrido, cobalt 2 would be the name of it. So the names change indicate the linkage. So this would be a linkage isomer, an example of linkage isomerization. Okay, next we have stereoisomerization. So in the case of stereoisomerization, we've got three kinds of, well, there are two kinds of stereoisomers. So one is called geometric stereoisomers, and there are two types of geometric isomers that we'll talk about. And the other type of stereoisomer is optical isomer. The main thing about stereoisomers is that the linkages, everything connected to the central atom stays the same. Okay, those don't change. But what happens is how they're arranged, how the ligands are arranged around the central atom. That's what changes. But right now, we're talking about stereoisomerism. We're not talking about the whole coordination compound. We're just talking about the complex ion. Okay, the stereoisomerism occurs in the complex ion. So there are two kinds of, actually there's a third kind here, do I have it there? So we have so-called cis-trans isomers in stereoisomerism part 1. So these are geometrical isomers. So there are two geometrical isomers. So let me separate this. So we're talking about geometrical isomerism. And the first type, I'll put A, is cis-trans isomerism. And the cis means that two ligands are on the same side of the molecule, and I'll have to show you some pictures to illustrate that. And trans means they're on opposite sides. Now this cis-trans isomerism, this also occurs in organic chemistry. And the meaning, again, I guess we could think of inorganic chemistry when we talk about cis and trans. I'll talk about, maybe I'll use the same analogy. I'll say it's analogous to these ligands. So ligands being on the same side, ligands being on the opposite side. So here's an example of cis-trans isomerism in square planar. So this only is going to occur in square planar and in octahedral. Okay, so it's not going to happen in tetrahedral. So you can't get cis-trans isomerism in tetrahedral structure. But in a cis isomer, here we have the two chlorines, two amines. So if you had all amines, it wouldn't work. If you had all chlorines, it wouldn't work. So not all complex ions can have cis-trans. There has to be a certain number of, there's only a very particular case. So the case has to be where you have to have two of one kind of ligand and all the other ligands are different. So if the two ligands that are the same are on the same side, so let's look at the chlorines in this case, or the chloros. They're on the same side of this square, so that makes this a cis isomer. If they're on opposite sides of the square, that's the trans isomer. So that's what we're talking about. They're on the opposite side. Now, you don't look at, we could use the amines in this case. So if you have three amines or three chlorines, you can't have cis or trans because, you know, the way they arranged around the this shape would be the same. So in tetrahedral, if you had a tetrahedron, you couldn't have cis or trans because remember the tetrahedron, the bonds point to the corners of tetrahedron, and if these bonds here were at the corner of the tetrahedron, it would be the same. So the difference is sometimes you can draw a structure that looks like it's cis-trans, but if you spin it around three-dimensionally, remember these structures are not rigid in space. You can actually, they're moving, the molecules can move in any direction. The best way to really visualize these, this isn't too hard to visualize in the square planar case, is with actually building an actual model. And I don't know, probably in first semester of general chemistry, maybe you did a lab or you did exercise, you actually built models to look at the structures when you studied the structural aspects of molecules. And I said that was in chapter 7.6. Okay, the other shape where you can have geometric shape where you can have cis-trans isomers is in the octahedral. So let me see if I can move this out. So we have geometrical isomerism and octahedral. Again, the cis and trans means the same thing. Cis means it's on the same side, and trans means it's on the opposite side. So look at these two structures. Which one would be cis and which one would be trans? Which one kind of looks like it's on opposite sides? Maybe that's the easiest one to identify. And I think it's this one. It looks like the chlorines are on opposite sides of the plane. If you look at the four amines, they're forming a plane around that cobalt. And then above the plane and below the plane are the chlorides or the chloros. And so that's the trans. So that's the trans there on the left. So this is the trans here. I'll put trans here. Trans. And then on the right, we have the chloros. Look like they're not on opposite sides. If they're not opposite sides, they're on the same side. So they're sort of on the same side. They're not exactly, but that's what we would call this. So they're sort of on, this is in the plane, but this is above it, but they're kind of near each other. And that would be called a cis. So another thing to look at is that in an octahedral complex, the ligands that are cis are separated by 90 degrees. This is a 90 degrees here. So this angle is 90 degrees. And the ligands that are trans, what's the angle here? The angle here is 180 degrees. Okay, so the ligands that are trans are 180 degrees in an octahedral complex. The ligands that are cis are 90 degrees in an octahedral complex. Let's go back and look at the square planar case again. And let's look at these, let's look at the cis and trans in terms of what is the bond angle between them. So in the case of the cis, the bond angle here is 90 degrees. In the case of the trans, the bond angle is 180 degrees in the square plane. All right, so let's continue. And this case is another example of cis and trans. And what this shows is that the isomers have different properties. So that's one thing. I didn't mention that, but all these isomers, when we talk about the linkage isomer, when we talked about the coordination isomer, they have different properties. And when we talk about cis-trans isomers, they have different properties. The properties could be, say, it could be a property like the melting point in the coordination compound. So the melting point. So if you had a nitrate out here or a chloride, the melting points in the crystal would be different. But in this case, it's showing one property is the spectral properties. The cis form of this cobalt tetra-aqua dichloro ion is violet, and in the trans form, it's green. So the properties are different, which means that you can easily distinguish one from the other. And when you name these, the names of both of these would be the same. Both of these would be a tetra. We call it a tetra aqua or tetra aqua dichloro cobalt and it'd be a cobalt dichloro cobalt 3 in this case. Cobalt 3. Both the names are the same. So how do we distinguish them? We distinguish them by putting cis in front of the left one. We use the same name, but we put trans in front of the name of the other one. That's how you distinguish the isomer. Okay, there's another kind of stereoisomer. This is a geometric isomer. So I said stereoisomerism too, but this is another kind of geometric isomerism. So it's called the FAC and MER stereoisomers. And actually, you'd write that in front of the names too. So this is how you distinguish them because the rest of the name would be the same. But these are stereoisomers that have more than two. So previously we said, well, if we have an octahedral complex ion and we have two of the ligands match, but all the rest are different, then we can identify cis and trans isomers. Well, if you have three ligands that are the same, then you can identify the facial and the meridional. So it's meridional and the facial isomers. So, and the example on the right is the facial isomers. Three ligands on the same side. So we have an octahedron. If they're on the same side of one of the octahedron faces, if you will, or planes. So the octahedron has 8 planes that form up this octahedron. So if 3 of the ligands form one of the planes, so we have chlorine, 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 chloro, 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 that would be a facial isomer. And again, let's look at these bond angles. The bond angle in a facial isomer are all 90 degrees. So the bond angles between all the chlorine, cobalt, chlorine, cobalt, chlorine, cobalt, chlorine, chloride, cobalt, chloride are all 90 degrees. So that's another way you could look at it. The other one is the called the meridional. Yes, I don't know how to pronounce that. I've never heard anybody say that before. These stereoisomers are new to me, so I haven't come across these before. But they are in. They're not in your book. These are in the homework. So when you get to the Newton, they're going to talk about these different isomers. So I put them in this lecture, so you at least have heard of them before. So again, you have 3 ligands that are the same. And in this case, if ligands are in a plane that transects the octahedron. So in this case, we have chlorine, chlorine, the chlorides, chlorides, or chlorochloros when they in the name. If you drew a plane between them, that plane, rather than be a face of the octahedron, it transects the octahedron. And if we look at the bond angles, it turns out that the bond angle between so we have 2 90-degree bond angles, and we have 1 180-degree bond angle. Whereas in the facial geometric isomer, we have 3 90-degree bond angles between the ligands. So that's how you distinguish them. Okay. So again, we'll encounter these in the worksheet. We'll be practicing these, understanding, recognizing these different kinds of isomers. The last stereoisomerism or stereoisomer we're going to look at are called optical isomerism. And the thing about optical isomerism is that these are really almost identical. they have one very subtle difference, but they have identical formulas. They have identical properties, chemical and physical properties, pretty much. So if you looked at melting points or solubilities, or how they react with other uh, compounds or elements, they're all the same. The one thing that they have different is how they interact with plain polarized light, and these are how they were identified. Otherwise, they're really hard to separate. It's really hard to identify them. It turns out that optical isomerism occurs commonly in biological systems, and so that's how they were discovered. Was the chemist was studying compounds obtained naturally from biological systems, discovered this optical isomerism. So they're called enantiomers, and a couple things. So we have a name. So these different optical isomers called enantiomers. Now that doesn't tell one from the other. So an enantiomer is a pair of optical isomers. That's what that is. So they're at the bottom of this. I said there's lots of ways to designate these optical isomers. So it's not as simple as like the FAC and the MER or the cis and the trans. I don't know, for some reason, there isn't just a single way to distinguish. I guess there hasn't been a standard established. And so I think on the next slide, I have someplace I have here. Let's see. I'm having trouble changing slides. I don't know why this happens. Let me get out of here. Let's see. Okay. Sorry about that. There we go. Okay. There we go. Okay. So here are the names. So they can be called plus or minus isomers. This has to do with how all these names have to do with what they're doing to the plane polarized light. I'll explain that in the next slide. But they could be plus or minus. They could be RS, DL, dextrolevo, or DL as applies to carbohydrates. So all carbohydrates, natural sugars, are one of optical isomer. In fact, all natural sugars are the D isomers. So the L isomers exist, but they're not natural. Okay, so that's just one example of optical isomerism in nature. So in nature, usually nature produces only one of the pair of optical isomers. Usually you don't get two. But in chemistry, if you made one of these molecules in the lab, you get both because the properties are so similar. So what do they do so what is plane polarized light, first of all? So natural light is called, has wavelengths in all directions. They just appear to, come at you from all angles, if you will. But if you put a filter called a polarizing filter right here in the path of the natural light, the filter is kind of like a grating. So it's a really fine grating that's on the order, same magnitude, same order. The spacing of this grating is the same, is like equal to the wavelength of the light. So it separates light. It only allows light through in one plane. And this is the same thing. You have polarizing sunglasses. It's made of a polarizing filter. So the light that hits your eyes is plain polarized light. So anyway, you get the polarized light. The light's coming through in only one plane. So this shows light is a wave. So this shows the wave in one plane. And it goes into a sample tube. And in the sample tube is your sample containing your optically active isomer, or one enantiomer, one of a pair of enantiomers. Remember, isomers, when we talk about isomers, you're comparing two different structures, one compared to the other. So you have one isomer, one active isomer in the sample tube. And when the light comes out, it's rotated. So, sorry about that. So it's rotated. So when it rotates, that's the property that these optical isomers produce, one of the properties they have. And so before the light comes in, it's in this plane shown here. After it comes out, it's rotated by a certain number of degrees called the theta. That's the number of degrees. So what the isomers do, one isomer rotates the light a certain number of degrees to the left, and the other isomer rotates the light a certain number of degrees to the right, so in an opposite direction. So each optical isomer rotates the plane polarized light in equal but opposite directions. So that's why I have the designation plus or minus. So if you say if it rotates one direction, that's a plus direction. The other isomer is going to rotate it in the minus direction. The D and L stand, those are germ words for dextro and levo. So dextro means to the right, levo means to the left. So that's where the dextro levo comes from. That's where the D and L comes from, and so forth. So that's what the designations mean. It's just that one isomer rotates the light one way and the other isomer rotates the other way. So how do I identify an optical isomer? Well, an optical isomer is a molecule that has a non-superimposable mirror image. An example of that, so I always said they're called enantiomers. A few terms. A mixture of optical isomers does not rotate plane polarized light. If you think about it, if one isomer rotates it one way and the other isomer rotates it the other way, if you have equal amounts of each isomer in a mixture, the light's not going to rotate either way. So that's why they're difficult to discover. It was only when one isomer was obtained from a biological source that the scientists noticed that it rotated plane polarized light. Actually, if you look at the structures, the crystal structures, the way it was discovered was from the crystal structure. You look at the crystal structures in one enantiomer, the crystal of one enantiomer is a mirror image of the crystal of the other enantiomer. So the crystal structures actually represent the molecular structure, this mirror image relationship between the isomers. So the mixture, an equal amount mixture, so this equal amounts of a mixture is called a racemic mixture. This is another term, and we'll revisit these terms. These optical isomers also apply to organic compounds. And like I said, they're common in biology, so they apply to organic compounds and biochemical types of compounds. So I guess this last statement, a pure optical isomer is difficult to obtain unless you get it from a biological source. But if you just try to make one in the lab, it's very difficult to do. So here's an example of a mirror image relationship. Our hands, like I said, in biology, there are lots of examples of mirror image relationships. So our hands are mirror images. In this figure, a person's holding up their right hand and their left hand, and the left hand is a mirror image. So if you look in the mirror of the right hand, this image of the left hand is identical. This image of the right hand, the mirror image of the right hand is identical to the left hand, right? But you can't superimpose one on the other. I guess I don't have an example of that, but you can't overlay one hand exactly over the other hand. So where do these mirror image isomers occur? Well, they don't occur. I'll say you where they don't occur. You can't have mirror image isomers in linear structures, in trigonal planar structures, or square planar structures. So they only occur in tetrahedral complexes and octahedral. In the case of a tetrahedral complex, all four ligands have to be different. Okay, so we have an example here of a complex ion with four ligands. We said A doesn't equal B doesn't equal C equals D. If any two ligands are the same, you cannot have an optical isomer. So it doesn't, they all have to be different. Every ligand has to be different. And this applies to organic compounds as well. And I think I said that. Same rule for organic compounds. So octahedral complexes. So they can exhibit mirror image isomers, optical isomers. So here's a question. Does COEN, so the EN, remember, is the ethylene diamine. It's this structure. It's the N like that. NH2, NH2. This is called the skeletal structure of organic compound. We're going to learn about that in the next chapter. We'll get to chapter 4. But that's kind of a one-way, shorthand way you can write the ethylene diamine ligand. So, so we have, remember the ethylene diamine ligand is a bidentate. So this has a coordination number 6. Because each EN has two ligands. So we have 2 ENs, so it's 2 times 2 is 4, plus the 2 chlorines is 6. So this coordination number 6, so that's octahedral complex. So can it exhibit cis-trans isomerism? Well, since it has 2 chlorines, we always saw that. We said, yes, there can be cis-trans. And if the chlorides, I should say chlorides, if the chloride ligands are 90 degrees apart, then it's a cis isomer. This is 90 degrees. Saw that before. If the chloride ligands are 180 degrees apart, it's a trans isomer. So yes, you can have cis and trans isomers in this complex ion. Does it exhibit optical isomerism? Well, the trans form doesn't, and we'll look at an example, but the cis form does, yes. So the cis, which has the chloride ligands at 90 degrees, does have a non-superimposable mirror image. But the trans form has a mirror image, but it is superimposable. It's not non-superimposable. So the better way to say it, not non-superimposable, better to say it is superimposable. So if the mirror image is superimposable, it's not an optical isomer. It doesn't have optical isomer. Okay, so here's an example. So here are the structures written out. So on the left is the cis form, and notice that the chloride ligands are 90 degrees apart. And on the left side is one, the complex ion cis form drawn one way. And on the other side is the mirror image. And you notice these bonds are coming up. So this bond, the wedge bonds are the same. If you look at these structures, you can imagine a mirror in between. So here's our mirror. This is our mirror. The structure on the left is a mirror image of the one on the right and vice versa. Well, it's hard to visualize this, but if you did make models, you'd find that you cannot superimpose one on the other. Okay, they are different. So they do have optical isomer. So you can say a cis form of any octahedral complex has optical isomers, and one is the plus isomer. I don't know which one. You'd have to do it. You can't predict which one is the plus isomer, which is the minus isomer. That's determined experimentally. And then on the right, we have the trans isomer. And the trans isomer, if we made the mirror image, we could draw the same thing, mirror image. But because it's symmetrical, the mirror image is superimposable. So it's not. So there's no, so we have optical isomers here. We have no optical isomers here. No optical isomers on the trans form. Now, another rule that you can use is if you can see a plane of symmetry in the structure, then there's no optical isomers. Well, clearly, if you look at this transform, there's a plane of symmetry right here. So the left side is equal to the right side. There's also another plane of symmetry that goes right, it's in the plane of the screen that you're looking at. The plane of symmetry that goes right through, I didn't draw that very well, but there's a plane of symmetry that goes right through the middle of the molecule this way. It bisects it. I redrew it. So everything on the front side is the same as the back side. So there's actually multiple planes of symmetry in this model. There's two, at least, two that I can see. So that means there are no optical isomers. If there's a plane symmetry, the mirror image is superimposable on the original image. So this plane of symmetry rule is important. So it's a plane of symmetry. And that's why, oops, plane of symmetry. Sort of wrote it there. That's supposed to be symmetry. So the plane of symmetry rule. That's why the linear and the square planar molecules don't have optical isomers, and why the tetrahedral structure has to have 4 different ligands. If it has 2 of the same ligands, then there's always a plane of symmetry. So here's another way to look at it, just another structure. On the left is the trans, and the mirror image of the trans. You can see you can just plop one on top of the other. It's identical. On the left is the isomer 1 and the mirror image of isomer 1. And then we have isomer 2, which is changed a little bit. And isomer 2 and mirror image are the same. And the way you can see, one way to get isomer 2 is you switch the attachment of the, say, this nitrogen is moved, the nitrogen and the chlorides here switch places to get isomer 2. And that's one way. If a structure does have an isomer, is an antimeric, does have a mirror image isomer that's not superimposable, if you just switch 2 of the ligands, you change from one isomer to the other. If you interchange 2 ligands, you change from one isomer to the other. Repeat that. So if you start with a plus and you interchange 2 of the ligands, you switch it to the minus. And I'm not talking about charge, I'm talking about the designations. Maybe I should say R and S or something. There's lots of ways to designate these isomers. That's rather confusing. You don't have to remember. Okay, I'll just keep those. And that's the end of the lecture. So I want to switch to the screen. So let me stop my share. And let me get these pens out of here. Okay, I'll stop the share. And let's look at the worksheet. So this is worksheet 34. And I think this front page just explains something about isomers and the different geometric shapes that complex ions can have. And so I think this top part is pretty useful. You might want to keep this for when you're doing your homework or your exam. It's just a summary of what we talked about. So the actual worksheet is on the next page. I'll flip that over. So I have 4 problems here, and these 4 problems represent 4 of the 5 different isomers that we talked about in the lecture. So I'll work a couple of them. I'll do the first 2 and I'll let you do the second 2. I do want you to turn this one in, I think. If you look on the module for chapter 19, I think this is one of the worksheets I want you to turn in. So I'll do problems 1 and 2, and I want you to do 3 and 4. Okay, so you try to do 3 and 4. That's for you to do. I'll do 1 and 2. So problem 1, it says, what kind of isomers are these? So let's look at those. So in this case, we have amine ligands. I'm going to zero in on it. We have the ammonia ligands. And we have, focus, come on. There we go. Ammonia ligands and a nitrite ligand. And the nitrite ligand is connected, the ammonia ligands are all the same. The nitrite ligand in one ion is connected to the nitrogen, and the nitrite ligand in the other ion is connected to the oxygen. So these are, these isomers are called linkage isomers. So it's a structural type of isomer. It's one of the, it's a structural, and the kind of structural isomer is the linkage. Okay, so that's what I wrote down. It's a structural isomer. It's the broad category, and it's a linkage isomer. If we go back to our sheet here, the kind of isomer it is right over here. So we have, it's a structural isomer because there are different bonds to the metal, and it's the linkage isomer. So it's this category, structural linkage. That's what I wrote down. Okay, so that's what I want you to do for this worksheet, to figure that out. It says write their formulas. So the formula, let's see, the first one is CO, so it's a complex ion, so it's going to be in brackets. So CO, and then we have NH3, and we have 4 or 5 of those. And then we have NO2 for the one on the left, and it's a 2 plus. And the other one is a cobalt, and it's an NH3, and there's 5 of those, and it's an ONO. That's why we write that to indicate the nitrito, and that's a 2 plus. This, what are their names? So we have pentamine nitro. So the NO2 is called the nitro ligand. Cobalt 3. So the nitro, the NO2 is, remember I said the nitrite ion? So let me just write that here. So it's a nitrite ion. So it's NO2 minus. Okay, that's what the NO2 is. So that's how we know, since the charge of the whole ion is 2 plus, that means the cobalt is a cobalt 3. And the second isomer, the other structural isomer, is a pentamine nitrito cobalt 3. And so they do have different names. They're different ions. They're structural. They're linkage isomers, I should say. And so that's the kind of isomer they are. The formulas are exactly the same. So the molar masses are the same, but their names are the same. Their structures are the same. So if you look at the structural formulas, you look at their names, you can tell that they're different. If you just look at the molecular formula, they're identical. This, the molecular formula, if we wrote the molecular, we have cobalt, we have 5 nitrogens, we have, actually we have 6 nitrogens, and no, we have 6 nitrogens, I'll put a 6 there. So we have cobalt, 6 nitrogens, 5 hydrogens, and 2 oxygens. So that's the formula. This is our formula. And we said, what makes these isomers is that the formulas are the same, but the compounds are different. So you could write them. We wrote out the formula for each ion. We write that a little differently, but the names are definitely differently, and then the structures are different. Okay, that's what makes them isomers. This is the same, but those are different. Okay, number 2, what kind of isomers are these? Well, let's look at those. These look like they're octahedral. So let's say they're octahedral, first of all. You have to recognize that. So it looks to me like they're mirror images, and this little dashed line looks like a mirror. So this one, see this has a nitrogen in front, chloride, ligand in the back, chlorine up here, nitrogen. So these turn out to be mirror image isomers. So these are stereoisomers. And since they're mirror images, they are optical isomers. So these are called optical isomers. So they're stereo optical isomers. And what else? They write their formula. So the formula would be, let's see, these are ligands. I don't know what the charge is. It could be an iron 2, or it could be, maybe it's a neutral substance, because if it's iron 2, it would be neutral. If it's iron 3, it'd be a +1. So I'm not sure what it is, but I can write this. So we have iron, I'll put it in brackets, because everything within the coordination, if you remember, is in brackets. So I'm going to put it in brackets. We have En, ethylene diamine 2, and chloro 2, but chloro alphabetically, let's see, the neutral. So ethylene diamine is a neutral molecule. So remember when we write the formulas, the neutral ones go first, and the anions go second. So this is En, just put En2, and then Cl2, and that's in brackets. So that's the formula. So the formula is the same. The way we would designate them is one would be a plus and one would be a minus. That's the easiest way to designate them. And remember, the plus and minus refers to the way it rotates plane polarized light. So I'm going to stop there and let you do the next. So there's the two other isomers, two others out of the 5 that we talked about earlier. And so you figure those out and then turn this sheet in. So that's all for now. I'm going to end this lecture, and we have one more lecture to do in chapter 19. And so I'll see you then. Bye for now.